Yeah, so in the last lesson, we went through the definition of a gas formation volume factor, both the dry and the wet, and we looked at the differences between those. We also saw that for a dry gas reservoirs, both of those expressions are the same because there is no condensate that comes out of solution at surface. And we also saw how the z factor was a part of that definition. So on that note or in that context, I find it appropriate to do a short recap on the so-called dry gas material balance equation that a lot of us have been exposed to in university many times, probably for some of you. And the reason why I do a recap here is that first of all, it's kind of the 101 of material balance engineering, which is widely used throughout the industry. So it's a good recap, call it from that engineering perspective. But it's also a good way to see where PVT properties can be applied and where it's used in a practical sense, and obtaining the output essentially of this exercise is the original gas in place for a particular reservoir, which is a thing that a lot of us relate to, not only reservoir engineers, petroleum engineers, etc., but also petrophysicists, geologists, CEOs, people communicating to investors, etc. So on that note, I think we'll just get to it. The basic assumption for the material balance equation is that we assume that there's a constant volume at time, a constant hydrocarbon pore volume. So in the reservoir, the volume is constant at time zero at initial pressure. And also after some period of time where you produced and depleted the reservoir pressure down to a new, call it average reservoir pressure. P average. To honor this assumption, you have to, as pressure is depleted, remove mass. So you have to produce surface volume to account for that. That's just because we know that when temperature and volume is constant and we reduce pressure, to remain at constant volume, you have to remove the equal amount of volume increase, if that makes sense. So the first assumption that we have to remind ourselves is that we assume, and that's a fairly common assumption in material balance equations, that the pore volume is constant. That's one of the constraints. The second is the definition of, or how we convert reservoir volumes to surface volumes, where this Vg g hat is the surface volume. And that's simply where we take the reservoir volume of gas and divide it by Vgw. This is applicable for dry gases or dry gas reservoirs. So if we take this constant pore volume assumption, or up here, that the hydrocarbon pore volume has to be the same, and we multiply the surface volume, or the so-called original gas in place, by the initial gas formation volume factor on the left side. And we, after a period of time where the pressure has been reduced and we have a new gas formation volume factor to account for that, but the hydrocarbon pore volume is the same. And we also know that the, call it remaining surface volume that we can get out of this reservoir, depleted reservoir gas phase, is G minus GP. When we're at that stage, we also have to remember the definition of the dry gas formation volume factor, which is Z times the standard condition pressure in absolutes, divided by multiplied with the reservoir temperature. Then we divide that by the standard temperature and reservoir pressure. So simply implementing or inputting that on each side of this equation, we get the following expression. And we see that when two things are equal on both sides of the equal sign, we can delete or remove those, and we get a simpler expression right here, which has, I think, four different yeah, 4 or 5 different symbols. And if we take that equation right there, divide by g, and solve by p over z, we get the following equation. That's very, very, call it common or famous, and is derived in a lot of the fundamental reservoir engineering classes, which says that P over Z is equal to minus the initial pressure divided by the Z factor at the initial conditions and the original gas in place, and then multiply that with GP, which is the cumulative gas produced at a certain point in time, plus the initial pressure over the initial Z factor. And in practice, how this is used is with the so-called P over C plot, where the y-axis is P over Z, and the x-axis is GP, which is just the amount of gas that you have produced. And then, engineers like myself, we love straight lines and XY plots. So you can then plot the pressure over the P over Z plot and different points that you measured through time on that particular plot. And the way you would get these properties is you would do a so-called well test. You would shut in the well. So that's probably a thing you can only do for conventional reservoirs, where you can actually shut in the well and get a pressure buildup such that you can get an accurate estimate of the average pressure at a particular point in time. Then you just simply divide that by the Z factor. The C factors you can get from a correlation or from equational state or similar, so that's readily available. The GP is just the amount of gas you produce. That's just doing counting at surface. And over time, these points will yield some kind of slope, and you can then fit a line through those points. And the point where it intersects zero is the original gas in place volume, or the estimated reserves that for that particular well or that reservoir or whatnot. And what happens when P over Z is 0, if we use this equation to the left here, and we say that it should be 0, we get essentially that this has to be equal to 0. We can then divide Pi over Zi on both sides of the equation, and we get that at that point Gp is equal to G. And we get this number that we were after. Good.